in the BioBankCloud project, and what we want is to provide a service to the people doing biobank and bioinformaticians. So the future of NGS is this kind of machine. We already have spoke about them this morning. What is interesting about, what is very important about this machine is their velocity. If we store the data they produce in Hadoop, we will have to store 45 megabytes of data per second. So the Illumina people recommend that you have a 1 gigabyte, one or two, yeah, link directly to Amazon EC2 to store your data. So this machine are producing a lot of data, and seeing the cost of them, you want to use them at their maximum, and so you will have a okay. Sorry. Okay. So, so you will have a lot of data, and you need to store them onto, yeah. So, and you want to have a lot of data, because the thing is that the more data you will have, the more accurate will be your analysis, and the thing is, so you want to build a big data set to be able to run a population analysis, and you have two ways to build a big data set. Either you have a centralized data set, and this is technically feasible, but this is politically hard because of politics problem, security problem. Do you want the, yeah, how do you ensure that confidentiality is kept if all the data are at the same place? Then there's a federated solution where you will have a lot of data sets that work together. It's politically feasible, but technically hard. How do you compare two genomes there on two data sets? How do you bring that together? So we decided to go for the technically feasible solution. And to use the tool we know work in for that. I'm a system person. I read paper by Google, Microsoft, and things like that. And their solution is big data. They analyze trillions of logs every day using big data. So what is big data? Big data first is commodity hardware. Commodity hardware you can buy for it. Yeah, every day. It's not very powerful hardware. It's not specialized blades that are very expensive. It's cheap. To give an example, we have this kind of rack where you put something like 40 hard drive in them, and you can have up to 180 terabytes of data in one box like that for less than $2,000. So it's quite cheap, and then you can have 8 of this, 8 rack of this. So 8 rack is something like between me and the wall, and you will be able to store 14 petabytes of data, which means something like 91,000 whole genomes. So we were speaking before about problem reaching the 60 terabytes of data. We see that not so much space. For less than $1 billion, we can store a lot more. So then you will tell me, okay, but we need sysadmin to manage that. But sysadmin, we don't need so many sysadmin. If we take the example of Facebook, they created, they recently opened a data center in Sweden. It's the biggest data center in Europe. It consumes something like 2% of Swedish electricity. And it's run by 35 employees, which means that each of these employees have to manage 20 to 26,000 servers. And just before we were speaking of 80 servers. So why can we do that? Because all the servers run the same software. All the servers run Hadoop that ensure that there is a separation between the users, that ensure that no user will be able to crash server by overusing them or things like that. And as they all use Hadoop, you don't have problem of a user wanting to install a software that breaks the compatibility with another software and things like that. So then it's commodity hardware. So it's not a very fast hard drive and things like that. And for example, if we want to read one whole genome, it will take 1,000 seconds. 1,000 seconds for one whole genome is very slow. As I said, Google analyzed trillions of logs in few seconds, so we can't work with this slowness. So what we do in big data is that instead of taking a genome and putting it in one hard drive, we divide it in blocks and put it on several machines. And now we can read the different parts of the genome in parallel. And so if you have 1,000 machines, you can read one full genome in 1 second. And now that we are speaking of reading one full genome in 1 second, we can start to think about doing population-based analysis, where we will compare thousands of genomes. So we have this big data solution, and now how do you execute them? Do you use that? And solution is to use system as a service provider. So, for example, Illumina is providing such a service, but there is other. I forgot the name on the result, but there is other provider in Beijing. Or the problem is that we can't use that in Europe because the law makes that if we put actual people genome in the system, they can't be stored somewhere in the US or somewhere in China. So we want to provide a solution for sequencing center or high performance center that allows them to work in-house with all this genome data. So our solution is BioBankCloud, and it's the user we target. There's 4 kinds of users. There is the IT administrator that will deploy and maintain the service. There is an ethic auditor that will verify that everything follows the rules of ethics and the rule of the frame of the European General Data Protection. And then there is biobanker and bioinformatician. So biobanker and bioinformatician are the 2 main users, and there are 2 very different users. On one side, we have the biobanker, which are basically the NGS data producer. They will produce the data, they will manage them, they will manage the metadata, and they are not programmers. On the other side, the bioinformaticians are the consumer of this data. They want to run analysis on the data, and they are programmers. I heard this morning that they may not be so good programmers, but they are programmers. They use Python, they use R, MATLAB, they do script to run the analysis. And then there's so you need a communication between these 2 entities, and this communication is not always very easy. So we want to make a tool that will allow them to work together. So also is BioBankCloud, and is composed of different parts. The dark blue part are parts that we today have as prototype level. The light blue part are part where we still have to work on to reach a prototype. I will, in the remaining of the presentation, I will go more in detail through the different parts of this solution, but just this is a storage. This is a scheduler, which ensures that we will not overload the machine. Personally, I'm working on the scheduler part. Then here we have a workflow, and we have everything. It's where the computation will take part. Will happen. And here we have our own solution, but it's running on top of Hadoop yarn, so you can run everything you want there. You can have Spark, you can have Adam, you can have Flink. We can add the block we want there when depending on what we need. And then here we have the BioBankCloud LIMS. So LIMS stands for Lab Information Management System. And it has several roles, but one of these roles is that all the data will be stored in the HDFS in Hadoop, and when we need to ensure security, we need to ensure that people can always only access the data for which they have the authorization to access. So for that, we have the LIMS that will build a kind of firewall around it. It's a G2 application, G2E application, so it's a web-based application, and the data will be managed by study level. And then, yeah. So what does it look like? When a user arrives, it's sign in. We have two-factor authentication, so that even if your password is compromised, we still have to steal your cell phone or to access to your special USB key to be able to connect to your account. And then when you enter in this account, you arrive on a page like this one, which on the right presents you the study you are part of, and on the left presents you a log of all the work modifications that have happened on the study you are part of. Now if we go in the study, you first have a team. It's all the people that have the right to, that are members of this study. So for example, the biobank people will be the master of the study. They will be able to say, okay, there is this bioinformatician that wants to do research on this data. We will give them access to the study, so we'll add them and give them a status as a researcher. So for example, this status will say that you can run computation, but you can't add new data in the study, or you can't remove data, or you can't copy them out, something like that. Then we have a browser where we browse the files that are part of the study. So basically, it's an HDFS file browser. We are adding some stuff to manage the metadata and to be able to search in it. So all of this is, then we have this metadata, we have this study, you are a member of a study, you can run an experiment. And how do you do it? No, sorry. I forgot, how do we upload the data to the HDFS, to the cluster? So either you have small amount of data, and you can just drag and drop or click in your web browser and it will upload them. But as we saw, this machine, Illumina machine, produce a lot of data. And so we want to stream that. And so for that, we can use Apache Flume that will be able to handle a big amount of data and to send them directly in the HDFS layer. And then we can directly start a pipeline that will do the alignment workflow and stuff like that from the data coming out of the Illumina machine. So then the researcher that want to run experiments on the cluster, they have also their own part, and they will basically upload the script that they want to run. They can select on which framework they want to run it, if it's Spark, if it's Adam, if it's and they run it, and then they go take a coffee or more if the the experience is longer, and they come back and the result will be there. So here I will give an example of experiment using our solution, the highway cuneiform solution. So basically, highway cuneiform is a workflow system where you will be able to run your data analysis workflow. So we took the example of variant call workflow. How it's done nowadays, done on one machine that do everything one after sequentially. So first the alignment, then the variant calling, things like that. And it's not very efficient because this machine is working as hard as it can, but it has the limit of the machine. And what we do is that we parallelize them, because it is very easy to break this into sub-work, where each machine will have a limited number of reads and will try to align on the sub-part of the reference genome. And this way we can scale. The more machine we will have, the faster we will go. And so as we scale, we can analyze more data, also do population-based comparison. So how does it scale? Optimally, we want it to scale linearly, so each machine we add each time we add machine, it go faster and faster. And we can't, I can't promise you that it will be linearly all the time, but we did it with up to 28 machines, and until now it has reduced the amount of time needed to run the workflow quite linearly. Yeah. 1 minute? Okay. So then the storage, we use HDFS. HDFS basically takes the file, break them into sub-piece, put the piece in a data node and have a name node that stores the metadata. So when you want a file, you will go to the name node, ask where is this file, and it will tell you read this block in this order, and you have the file. We have our own solution for this. It has the advantage to scale more and to add some tools such as erasure coding that allow us to reduce the footprint of each file, so that you can store more genome in the same amount of storage space. Just a point on the security. If someone, the data are not encrypted because you want to be able to run the analysis on the data node. So, but the thing is that this block, they are all mixed on the different nodes, and the logic is in the name node. So someone that compromises this node will just have a big pulse without any clue of how putting the thing together. So to compromise the system, you need to compromise the name node, but then we can ensure that the name node runs only the name node software, and is very difficult to compromise. Finally, we have this system that, and you want to deploy it. What we propose is a platform as a service. So we propose a tool for the IT people that they can define what each node will run, what software each node will run by simply drag and dropping the different software, and then they click on launch the cluster, and it deploys the cluster, install all the software, either on EC2, Vagrant, or bare metal systems. So as a conclusion, with BioBankCloud, we propose an open source commodity hardware NGS data management solution. And as I saw, it's based on a big data solution, which make it quite cheap. The status of the project is we will have a first beta release soon. How soon? It's quite soon, because on the 19th and 20th of February we have a workshop in Stockholm, and during this workshop, the second day will be a hackathon where people will basically be able to take in on the system and try their own usage, or develop their own blocks to add in. So thank you for your attention, and I want to thank the other people working on this project, so people from Stockholm, KTH, or Karolinska Institute, but also people from Berlin with the Humboldt University and Charité University, and from Lisbon. Thanks.
Really looking forward following this project and making note of that workshop also. We are a bit too short on time now, and we need all to have lunch. So please put your questions to Gautier outside in the lunch. Lunch. I'm hoping lunch should be outside. That's where we ordered it, and we're coming back here again at 1.